Hello class, Mr. King. We are going to move into part 2 of solving trig equations, and we'll look at inequalities today. Your assignment will probably be a practice sheet, possibly 2 practice sheets over a few days. Just as a reminder, you can come back to these notes and review this methodology, solving trig equation analytically. We've got a number of things to look for here. I'm not going to review them all now, but you are welcome to come back and look at these. You can always pause the video and read over these again. And these are probably in the PDF of the notes on part 1 as well. And then solving a trig equation graphically, of course, using technology, using your calculator, using Desmos. Again, those are reminders. So let's go into our first example here on the next page. So first of all, trig equations and inequalities can be more complicated. We can run into situations where we have half angles or multiple angles, also known as half numbers or multiple numbers. And so we're going to need the formulas, the identities we learned earlier, quite possibly. We might need to use other methods like squaring both sides of an equation. And some combination might be necessary. And we always, as we do in math, need to look for patterns. So in our first example here, we're going to look at a trig equation that obviously has a double angle in it. Cosine of 2x is cosine of x. And thankfully, the solution is domain constrained between 0 and 2 pi. Open endpoint, on 2 pi, closed on 0. And one of the things that we want to do in a situation like this is we want to get rid of the double angle because we're solving for x. And so in this particular instance, what we can do is we can use the identity that says that 2 cosine squared x minus 1 is equal to cosine of x, because 2 cosine squared minus 1 is what cosine of 2x is equal to. And so quickly we can see that we have now got an equation that's only got x as an argument of our trig function, the cosine. And now this is going to be a little bit easier, a lot easier. And so we're going to bring over the cosine of x to the left side of the equation by subtracting it like this. And at this point, we can see a quadratic form. 2 cosine squared x minus cosine of x minus 1. If you think about it, if we were to do a formal u sub, we could say u is cosine of x. And then we would get 2u squared minus u minus 1. And we could do a quick guess and check factoring on this because minus 1 is such a simple number to have on the end here. It's only got 2 factors, 1 and negative 1. And so 2u plus 1 times u minus 1 would, of course, be the factored form here. And we could check that quickly by doing the OI test, which is the outer and inner product, to see if we would get back to minus u. And we do. And the first terms give us 2u squared, and the last terms give us the negative 1. So this does work, and that's good. So that means that 2 cosine of x plus 1 times cosine of x minus 1 equals 0 is our factored form of our equation. And we can set these two factors equal to 0. And when we do that, we will quickly get to some solutions for x. This one I'm going right to the second step. If we know cosine of x minus 1 is 0, then cosine of x must be 1. And in this case, we know that cosine of x must be equal to negative 1/2 if we were to subtract 1 and then divide both sides by 2. So we can now determine what angles will work here. And again, I want to remind everyone that we are constrained where we're going to look for answers, which is thankful. Otherwise, we would be writing a formula for infinite numbers of answers. It different coterminal angles. In this case, for cosine of x, let's remember our trig circle. If we've got a cosine that's negative half, we need to be in the second quadrant or the third quadrant. And for cosine of x equal to 1, there's only one place where that happens, and it's here at 0 radians or at 2 pi radians. Of course, 2 pi is out, not allowed. So it looks like we're going to have three answers here. If cosine of x is negative half, we're somewhere in here, and that looks like a 2 pi over 3. Remembering our trig circle, if you're a little rusty, go back and look at it. And then the other angle is 4 pi over 3. And then x must be 0 over here if we're going to have cosine of x equal to 1. And so we have our three solutions to this first trig equation that involved a double angle in this case. Now we can move on to solving the associated inequality cosine of 2x is less than cosine of x over that same domain constraint. And we're going to use the calculator to graphically determine the solution. We already know where any intercepts will be. So I've already graphed this down below, so let's go take a look at this. But let's remember, okay, cosine of 2x is less than cosine of x. Well, this graph is cosine of 2x minus cosine of x here. Why? That's what we've graphed. And so if this were to be less than 0, well, that means we need to be looking at the range of angles where the graph is down below here. And you can see I've already got the 2 pi listed here, and of course 0 is over here. So from this graph, we can fairly readily see that from 0 to 2 pi over 3, in union with 4 pi over 3 to 2 pi, we'll solve that inequality. So coming back up to our problem, we can now write our solution when x is on 0 to 2 pi over 3, open interval, in union with 4 pi over 3 to 2 pi, again an open interval, we have our solution to when the cosine of 2x is less than cosine of x over 0 to 2 pi. Now, if we go down and look at the next inequality, it's cosine of 2x is greater than cosine of 2x. And in this case, we're going to look at the same graph again, but this will not be our solution anymore. Our solution this time will be when the graph is above the x-axis, we will have to go from 2 pi over 3 to 4 pi over 3, because this inequality is no longer greater than or equal to. This inequality is greater than, like so. And so this time we're going to go from 2 pi over 3 to 4 pi over 3. So we can now write when x is on 2 pi over 3 to 4 pi over 3. And you'll notice we're using exact radian angle measures here, which we did determine earlier when we were solving the equation and getting the exact solutions. These are exact solutions. Most calculators will not give you 2 pi over 3 or 4 pi over 3, but the TI Inspire will and Desmos will. I did this with Desmos. You may recognize the type of graphing screen as well as the controls over here. Now in our next example, we do not have a half angle or a double angle, but we're going to introduce a double angle, surprisingly, which you may not have expected we do. For sine of x cosine of x is square root of 3 on 0 to 2 pi. This is a typo. Fix that. And so what we're going to do is we're going to let 2 sine of x cosine of x come in here, and I'm showing you this so it doesn't get confusing to you. And I'm going to multiply that by 2. The reason I've broken the 4 apart into 2 factors is because we know that 2 sine of x cosine of x is 2 sine of 2x. So we're going to get 2 sine of 2x over here. And of course this is still equal to square root of 3. And then we'll get sine of 2x is equal to square root of 3 over 2 after we divide. And what's kind of neat about this is that we know that there are certain angles that will give square root of 3 over 2 as a sine value. And these angles, of course, are in quadrants 1 and 2, where the sine is positive. And one's going to be over here, and one's going to be over here, at pi over 3, 2 pi over 3. However, notice something. We're going to be solving for 2x, not x. And so we're going to go back to the beginning where we were originally with an equation just solving for x. And that is our goal still. X was constrained. Let me say that again carefully. X was constrained in this problem, not 2x. So we need to see how 2x is constrained. And so what we'll do is we're going to double the x. We're going to double the 2 pi. And we're going to double 0. It's still 0. And so we see that 2x is constrained between 0 and 4 pi. This may be interesting. It's going to be different than the last time. So what we now know is that 2x can be equal to pi over 3. It can be equal to 2 pi over 3. But we've got to keep going towards 4 pi. And so coterminal with pi over 3, another 6 pi over 3 gets us to 7 pi over 3. And then 2 pi over 3 plus 6 pi over 3 is 8 pi over 3. And we have, therefore, 4 solutions. Now, if we divide by 2 to solve for x, we're going to see that pi over 6, 2 pi over 6, which is pi over 3, 7 pi over 6, and 4 pi over 3. These are the solutions. And notice, if we think back to our original constraint up here, that we're between 0 and 2 pi, we are good. It works. We're fine. And that's how that works. We're going to solve the associated inequality 4 sine of x cosine of x is less than the square root of 3 by going to the grapher. So let's look at the graph below. What I've done is brought everything over to the left. So the equation, or the function that is y sine of x cosine of x minus the square root of 3. And what I'm looking to here is that the zeros are the solutions to this equation. And you'll notice that pi over 6, pi over 3, 7 pi over 6, and 4 pi over 3, those show up on the graph, and those are the solutions that we found a few moments ago analytically. And these are the exact solutions. With the graph, we can now find out where the function is less than 0 in this case, and that corresponds with 4 sine of x cosine of x being less than the square root of 3. And I'm going to use a different color for this. I'm going to use a bright pink, and we're going to be going from 0 radians right here up to pi over 6. We're going to be going from pi over 3 all the way over to 7 pi over 6 here. And then we're going to be going from 4 pi over 3 over to 2 pi, which is right there. And of course, we since we're less than, we're going to have open endpoints at all of these places, at 0 to pi over 6, from pi over 3 to 7 pi over 6, and from 4 pi over 3 to 2 pi. And this is how we are going to form our solution now. I'm going to use a slightly different way of writing the solution, which is perfectly valid, maybe a little more mathematically sophisticated, you might say. So we're going to go from 0 to pi over 6. We're going to say this, and I'm just going to add, because I'm teaching, from the graph below, we see that the solution set is x on, and we're going to be going from 0 to pi over 3. And I'm going to just sneak up here and look at the exact values from the solution to the equation. And this is with the union of pi over 3 to 7 pi over 6 in union with from 4 pi over 3 to 2 pi, all open intervals. And this is our solution to the inequality. Now, there's an allied inequality, which is if we let 4 sine of x cosine of x be greater than the square root of 3. And we can look at the graph again. Well, let's look at the graph again. And I'll change the color again here. We'll go to an orange. And this time we can see that we're over here above the x-axis and over here above the x-axis. And we can see pretty quickly that everything except for what we just wrote for our intervals is a solution. This time we have 2 intervals. And so if we look up here to what we answered in 2b, we can see that we're going to be going from pi over, not quite like that. Did I make a mistake? Let's see. Pi over 6 to pi over... Oh, this is what happened. You guys see that mistake? This is pi over 6. Okay, I'm glad I caught that. That's 0 to pi over 6. And then we go from pi over 3 to 7 pi over 6. And so let's make sure that's 7 pi over... Yes, it is. Okay, now we're good. So now what we can see here is that we're going to be going from pi over 6. So this is x is on pi over 6. Again, open intervals because we're not equal to pi over 6 to pi over 3 in union with 7 pi over 6 to 4 pi over 3. And we have our solution.